Video Lab Report 3, Group 3B. Our question was, how does force and kinetic energy change when applying different masses on strings off of a pulley? Does this work energy theorem hold true? The prediction that we had was the larger the mass will exert a larger force on the IO-lab, and the work energy theorem will hold true. For this experiment, 200 grams was added to the top of the IO-lab to make sure it kept in contact with the table. From there, 3 different masses were attached to a string on a pulley. The weights were then dropped, and the string pulled the IO-labs a distance of 0.65 meters. The pulley was used to get a constant force, and the IO-lab measured the velocity and the force. This system schema shows the IO-labs, weights, and the Earth all acting upon each other. The IO-lab is being pulled by the tension force from the weights are being pulled by the gravity from the Earth, and then the IO-lab is also acting upon by the gravity from the Earth. The free body diagram shows the forces acting upon the IO-lab. The acceleration due to gravity is balanced equally by the normal force of the table. In this experiment, we did account for friction, so there is no resistive force in the free body diagram. There is the applied force acting in the left direction caused by tension.
The experimental design. The experimental design consisted of elements used to gain data. These elements were the IO-lab software. We found kinetic energy to get work. We calculated the force times the distance to get work. The distance was 0.65 meters. Force was given by the IO-lab software. We used the max constant force to calculate the force times distance, and the delta kinetic energy was calculated using the max velocity. The flaws within the design were that we did not account for friction, the force varied greatly throughout the trials, and the wheels on the IO-lab may have slipped, not giving us an accurate velocity. The calibration on the IO-lab could have been off because the force didn't return to zero as it should have. We should have also taken the integral of force times distance to get a more accurate reading instead of just taking the maximum force.
For the results, we made 3 graphs of force over time and velocity over time for each one of the weights that were dropped. As you can see, the magnitude of the force and velocity increases as you increase the weight that was dropped. We picked the velocity to calculate delta KE with the max velocity shown on each graph. And we also picked the magnitude of the force that corresponds with the same time as the max and velocity. So to calculate work in the 2 different ways that are possible, we added up the mass of the IO-lab and the 200 grams that we added to the IO-lab, which was 0.403 kilograms for all 3 trials. The distance stayed constant at 0.65 meters for all 3 trials, and the forces for each one of the trials was found from the graphs. The velocity was also found from the graphs. So for the first trial, we had 0.1 kilograms dropped, which we plugged that into the delta KE equation, which delta KE was 0 initially, and we ended up getting 0.453 joules. And we did that for all 3 trials, and then to find work using force times distance, we did the force that was calculated using the IO-lab software times the distance, which was 0.65 meters, which equals 0.4875 joules, which was very similar. This same calculation was done for all 3 trials.
Scientific reasoning. Our scientific reasoning was to compare the delta KE to the force times distance. The work energy theorem tells us that delta KE should be equal to force times distance. This wasn't exactly the case in our trials because we didn't account for friction in our calculations. Another thing that could have gone wrong was the wheels of the IO-lab may have slipped when pulled by the dropping weight, which could have skewed our velocity data. Even with friction being excluded from the calculations, the delta KE and the force times distance were almost exactly the same. Additionally, the calibration of the IO-lab could have been off, which would account for why the force did not return to 0 every time. Taking the integral of the force times the distance would have been a better method to calculate the proper work in a real-life scenario. However, when we did this in our design, it did not give an appropriate value for the delta KE, which means that the work energy theorem would not have been correct. In conclusion, when you increase the mass acting on the end of the string, it will increase the magnitude of force applied on the IO-lab, and it will also increase the magnitude of the velocity of the IO-lab. The work energy theorem would most likely hold true if there were no friction in the experiment.